So, what if the next giant leap in AI doesn't come from just making models bigger, but from making them fundamentally smarter? Today, we're going to dive into a new paper that's proposing an AI architecture that doesn't just copy what a brain does, but actually mimics how a brain is organized to think.
Look, we've all been blown away by what large language models can do, right? They write code, essays, you name it. But here's the huge question this research kicks off with. Are they actually reasoning? The big idea here is that for all their power, LLMs have this deep architectural flaw that's holding them back from real, genuine thought.
Okay, let's get into this. The paper argues that even the biggest AI models today are kind of paradoxically shallow. You see, their core architecture, the transformer, has a fixed depth. And what that does is it puts a hard ceiling on how complex of a problem they can solve. They can't just, think harder or spend more time on a problem to crack it. So how do LLMs work around this limit? Well, they use a trick called chain of thought. The paper calls this a brittle crutch, and I think that's the perfect way to describe it. It's basically forcing the AI to think out loud, one word at a time. This whole process is external, it's slow, it needs an insane amount of data to learn, and if it makes just one tiny mistake along the way, the whole chain of logic can just shatter. The ideal, on the other hand, is latent reasoning. This is what our brains do. The thinking happens silently, internally, in this hidden computational space. It's fast, it's robust, it's efficient, and the goal is to finally build an AI that can do that.
So if the current approach is kind of a dead end for deep reasoning, where do we look for a better one? Well, the researchers turned to the best problem-solving machine we know of, the human brain. Let's see how they used it as a blueprint for a whole new kind of AI.
It turns out our brain's blueprint for complex thought really relies on three key principles. First, it's hierarchical. You've got high-level parts of your cortex that handle the big picture, the grand strategy, while the low-level parts are busy managing all the nitty-gritty details. Second, there's a separation of speed. Some parts of the brain think slow and deliberately, while others are super fast. And third, it uses these recurrent loops, basically thinking about things over and over to refine ideas and plans.
All right, let's move to the model itself and see how this all comes together. Say hello to the Hierarchical Reasoning Model, or HRM. It's designed to directly mimic that brain structure. It's got a high-level planner. Think of it as the manager. It's slow, deliberate, and it figures out the abstract strategy. Then you've got the low-level worker. This is the specialist that's super fast and just crunches the numbers. The planner sets a goal, the worker executes, reports back, and this cycle just keeps going, letting the model think deeper and deeper about a problem.
So the theory is beautiful, right? It's inspired by neuroscience. But does it actually work? This is where things get really, really exciting. The researchers put their tiny 27 million parameter model up against today's AI giants on tasks that were literally designed to be impossible for them.
And the results, well, they were stark. On these really complex puzzles like extreme Sudoku or finding the single best path through a giant maze, stuff that requires deep, sustained logical thinking, the state-of-the-art large language models using chain of thought just fell flat. Their accuracy, 0%. Just let that sink in for a second. On these incredibly difficult reasoning tasks, the most advanced models out there couldn't solve a single one. Not one.
So, how did our little brain-inspired HRM do? Let's check out the ArcAGI Challenge, which is a benchmark meant to measure general intelligence. The tiny HRM, with no pre-training at all, hits over 40% accuracy. That's way better than much larger cutting-edge models like Claude 3.7. A huge win right out of the gate.
But this is where it gets absolutely wild. Remember those extreme Sudoku puzzles where the giant scored a big fat 0? HRM solved them with 55% accuracy. It actually learned the deep, recursive logic of Sudoku from just 1,000 examples. Incredible!
And the story keeps getting better. What about finding the perfect path in a really hard 30 by 30 maze? Again, the big models, 0%. HRM? It found the shortest possible route almost 75% of the time. I mean, this isn't just a small improvement. This is a completely different league of performance.
And to really appreciate how mind-blowing these results are, you have to look at the numbers behind this model. HRM has just 27 million parameters. That's a rounding error compared to the billions or even trillions in today's LLMs. It was only trained on 1,000 examples for each task. It had 0 pre-training on the entire internet, and nobody fed it any chain of thought examples to copy. It learned how to reason completely from scratch.
So here's the crucial point. The performance is groundbreaking, for sure, but the why behind it is even more profound. The real secret here isn't just what the model is doing, but how its internal wiring spontaneously organized itself while it was learning.
To get this, we need a quick concept from neuroscience called neural dimensionality. The easy way to think about it is as a measure of how flexible a part of the brain is. A higher dimensionality means it can handle a huge variety of complex, abstract ideas. It's a generalist. A lower dimensionality means it's really specialized and focused on one specific job.
And here it is. This is the core discovery of the paper. When the researchers peeked inside the trained HRM, they found this exact brain-like structure had emerged all on its own. The low-level worker module, it developed a low neural dimensionality, becoming a focused specialist. But the high-level planner module developed a much, much higher dimensionality. It had spontaneously created a flexible, abstract thinking space, just like the prefrontal cortex in our own brains.
But here is the most incredible part. This brain-like organization wasn't programmed in. Nobody forced the model to do this. It was an emergent property. The model figured out, all by itself, that the most effective way to solve these hard problems was to organize itself like a brain, with a flexible planner and a focused worker.
You know, the authors themselves sum it up perfectly. They conclude that this model represents, and I'm quoting here, a viable alternative to the currently dominant chain of thought reasoning methods. It's not just another small step, it's a whole new path forward.
So what's the big takeaway from all this? We could be looking at the first real glimpse of a new paradigm for AI, one that's based not on brute force scale, but on elegant, efficient, brain-inspired design. And that leaves us with one final, massive question. Is this the architecture that will finally unlock true artificial thought?